It's another chemistry class. It's loud around here. I pray you're able to get so much noise in the school. That is me introducing myself again. I'm Oris, your ordinary teacher. My specialty is maths and physics. You're welcome to Science in the Fourth Dimension. I do physics and mathematics here at Bohr International School. But we're doing chemistry presently. What we're doing is chemistry today. We're still going on further into the introduction of chemistry. We're at part 6. For part 1, this is now atomic structure. Part 6, atomic structure. Although an error, the word atoms means indivisible. Atom means indivisible. Until the late 19th century, the atom was thought to be indivisible. However, several evidence now proves that atoms are made of particles. These particles are electrons, protons, and neutrons. Like you can see there in the structure. In the nucleus, you have neutrons, protons. Then outside the nucleus, you have electrons. So the name of atom is actually an error because the atom is actually divisible. I'm going to talk about models of the atomic structure. The first is J.J. Thomson's model. He proposed this model of the atom in the late 19th century, before the discovery of the nucleus and the modern understanding of atomic structure. His model is often referred to as the plumipodal model, and it was proposed in 1904. That's after he discovered the electrons. Later on, he went on to discover protons. So in his mind, it just felt like he has to draw something that will contain just the electrons and protons. You see the diagram there. You have the positive sphere, and then you have negative electrons dispersed throughout it. Thomson's model, while groundbreaking at the time, was eventually replaced by more accurate models. Experiments and discoveries were made which it could not explain. That was the trouble with Thomson's model. The model faced challenges with the result of the gold foil experiment conducted by Ernest Rutherford in 1909, which led to the development of the nuclear model of the atom. That's Rutherford's planetary model, and that's going to be the next model we'll talk about. But let me explain the gold foil experiment. Thomson's model could not explain the results of the alpha particle scattering experiment conducted by Ernest Rutherford. The expected even distribution of positive charge throughout the atom, as proposed by Thomson's model, did not match the observation of concentrated positive charge at the center of the atom. That's the gold foil experiment. You see the alpha particles passing through the gold foil. Part of it was deflected slightly, and part of it was deflected backward, which is not supposed to be, because the alpha particles are heavy. We're supposed to just pass through without coming back. This is a better arrangement of it. So when we have a central nucleus, those ones close to the nucleus can be slightly deflected. Those ones that are going to hit the nucleus will be deflected backward, and those that are far away will pass through without being deflected. That's the figure you are seeing there. Rutherford's planetary model is the next. The gold foil experiment conducted by Ernest Rutherford in 1909 led to the development of the nuclear model of the atom. This model proposed a small, dense nucleus at the center of the atom containing positively charged protons with electrons orbiting around the nucleus, like we saw in the diagram or the figure that we just passed. Now you can go back and check for it. Rutherford found out from his calculation that another particle, as the neutron, was supposed to be in the nucleus apart from the proton. So he proposed and predicted all the properties of what? Of the neutron. And when neutrons were discovered, it was found to be true. That's the atomic structure, Rutherford's model, planetary model. Over there, you can go through, you can pause and then check it through. You have the nucleus, central nucleus, and then electrons revolving around it. Right? The planetary model of the atom proposed in 1911 envisioned the atom as a miniature solar system. The atom consists of a small, dense, and positively charged nucleus at the center with electrons orbiting around it in fixed paths, similar to planets around the sun. This model contributed immensely to the understanding of the atomic structure. However, it could not explain the classical electromagnetic theory. That was the problem with Rutherford's model. Niels Bohr came and explained why Rutherford's model had a problem with the classical electromagnetic theory. According to the classical electromagnetic theory, an accelerating charge loses energy. This phenomenon is known as radiation of electromagnetic waves. electrons are charged particles, and moving in circular paths is expected that they accelerate. So since they are accelerating, they should lose what? They should lose energy. But why exactly does the electron not slow down? That was a problem that Rutherford's model could not explain. So Niels Bohr used the quantum theory to explain the challenge, because the electrons they obey quantum theory, which is higher than the classical electromagnetic theory. They can disobey the classical theory. According to the quantum theory, certain physical properties such as energy levels and angular momentum are quantized, meaning they can only take on discrete values. They do not change continuously, unlike what now? The classical physics, which allows for continuous values. Hence, electrons can only move from one energy level to another when they receive specific amounts of energy, not continuous. They get excited moving to a higher energy level. Electrons do not remain excited for long before returning back to their ground state. Bohr's intervention explained Rutherford's model, but it also had its limitation. It could not explain the structure of heavy elements with overlapping orbitals. That was a problem with what now? With Bohr's explanation. Quantum mechanics model. This is actually the current model of the atom, and it's based on quantum mechanics. It is also known as the Electron Cloud model or wave function model, sometimes called wave mechanics model. This model builds upon the principles of quantum theory and provides a more accurate description of the behavior of electrons in an atom, some of which are the Electron Cloud. Instead of specific orbits, according to Rutherford, electrons are described by probability distributions called orbitals, not orbits, orbitals. These orbitals represent regions in space where electrons are likely to be found. The Electron Cloud gives a more realistic depiction of the electron's position and momentum. Orbits talk about specific parts, orbitals talk about what now? Regions, where does the electron can be found. Quantized energy levels. The concept of quantized energy levels for electron is retained from the Bohr model, but instead of fixed orbits, such electrons are associated with specific energy levels and sublevels within the Electron Cloud, uncertainty principle. This was formulated by Werner Heisenberg. It's fundamental to the quantum mechanical model, stating it's possible to simultaneously know the exact position and momentum of the particle. Don't go further until you understand these basics. Go over everything again. Feel free to ask questions. You can send them directly to me or any means you want to send the question. Now look at the Bohr's model on one side, and then we have the wave mechanics model on one side. We check Bohr's model. Bohr's model had specific parts. That's in there. That's Bohr's model actually explains the Rutherford model. But if you check on the wave mechanics model, you realize that the first energy level has no business with the second energy level. Second energy level has no business with the third energy level, but the third energy level overlaps. So you see 4s coming before 3D. The fourth energy level also overlap. You see 5s coming before 3D. And then the fifth energy, they just overlap. The other models cannot explain this. So you just you take time and go through everything. So watch out for the atomic structure. I'll see you in the next class, part 2.